Morning all, back again. I've had a few requests from people in my class for topics that we've done previously in the year. So as we're doing stuff that's current, I'll also try and fill in a few gaps if you're struggling with any topics throughout the year. If you've got any questions or if there's anything particular that you want to see, just send me an email. I'll put my email on at the end of the video. Okay, so one thing that's often comes up and often people are a little bit confused about is co-transport. And in the first year A-level biology, we look at co-transport in terms of absorption in the gut through the epithelial cells from the lumen, which is shown up here. So the lumen is the pathway that the digested food takes down through the well, this is all happening in the ileum, in the small intestine. Okay, so here's the lumen. By the time the food reaches the lumen, reaches the ileum, it has already been digested. So starch has been digested first into maltose, and then I may do a video on this at another time, but you might remember that those disaccharidases, such as maltase, exist in the epithelial membranes, so in the microvilli of these epithelial cells. Proteins are being hydrolyzed down into amino acids. By the time we reach the ileum, that's where this absorption takes place. In the upper six, we'll look at, when we look at the kidney, we'll also see that co-transport plays a role. I'm not going to focus too much on that for now though. Okay, so I'm going to give the example of glucose being absorbed, but the same principle applies for amino acids. So, just add glucose molecule there. Okay, so until the absorption can take place by facilitated diffusion for a certain period in the small intestine, but that stops once the concentration gradient of glucose from the lumen becomes equal to the concentration of the glucose in the epithelial cell in the blood, so when we reach that equilibrium. From that point onwards, there needs to be the active transport, essentially, or indirect active transport of glucose from the lumen and eventually into the blood. That's important because obviously that glucose is really valuable. The body's putting a lot of effort into producing the enzymes to digest carbohydrates, to produce the glucose. It's necessary to absorb all of it. Okay, so the epithelial cell has some adaptations. I'm not going to spend too much time on this, but you would expect these epithelial cells to have lots of mitochondria, and those mitochondria are necessary to produce ATP through aerobic respiration, and that ATP is going to be important for this protein down here, which is called a sodium-potassium pump. And that's where I'm going to start this explanation. You'll see in some textbooks that the sequence of events is numbered. Often that sequence begins up here, but I find it a bit more intuitive if you start at the sodium-potassium pump. So you probably guessed that the sodium-potassium pump, well, it exchanges sodium and potassium ions, and in your responses in the exams you must refer to those as ions rather than just sodium or potassium, because we're not talking about lumps of metal that are being transported. So the sodium-potassium pump actively transports sodium ions out of the epithelial cell. At the same time, it actively transports potassium ions in. Now we're not really worried about the potassium ions, it's the sodium ions that we are really interested in. So, as those sodium ions are actively transported out, as you'll know, that's going to require ATP. So ATP is hydrolyzed down into ADP, an inorganic phosphate, and that provides the energy to allow this active transport. So where we see the red arrows here, this is active transport. So code transport is referred to as indirect active transport. This is the active transport part. We'll now have a look at how the glucose is moved from the lumen and into the epithelial cell. As those sodium ions are actively transported out, that lowers the concentration of sodium in the epithelial cell. So what we end up with here is a lower concentration of sodium ions. Now I'm using those square brackets as a shorthand for the concentration. So there is a lower concentration of sodium ions in the epithelial cell because of that active transport of the sodium ions at the sodium-potassium pump. That creates a sodium ion concentration gradient because through the lumen there is a higher concentration of sodium ions, and that's important. That's probably the most important part of all of this, that maintaining that concentration gradient is what allows the glucose to be transported from the lumen and first into the epithelial cell. So the sodium ions move from the lumen down their concentration gradient through this protein here. And this protein is known as, well, we could call it a co-transport protein. Sometimes you'll see it written as a symport. Okay. So sodium moves down its concentration gradient from the higher concentration in the lumen to the lower concentration that's being produced by the sodium-potassium pump. Now the movement of the sodium down its concentration gradient allows for glucose to follow. So really here, glucose is moving from a lower concentration to a higher glucose concentration. And that's only able to happen if these sodium ions move down their concentration gradient through this co-transport protein or symport. Now we've got an accumulation, that higher concentration of glucose in the epithelial cell. The glucose needs to move from the epithelial cell into the blood. So the blood is constantly moving through capillaries close to those epithelial cells. That means that there is a lower concentration of glucose maintained in the capillaries. So we've got a lower concentration of glucose in the capillaries, higher concentration of glucose in the epithelial cell, and therefore glucose is able to move by facilitated diffusion out of the epithelial cell into the tissue fluid, and once it's in the tissue fluid it then moves from the tissue fluid and into the capillary. So let's just fill in some gaps here. These blue arrows represent facilitated diffusion. The green arrow represents co-transport. This is a carrier protein here. And I think that is everything. So that's co-transport. Just to reiterate the key points. The sodium-potassium pump creates this concentration gradient of sodium ions between the lumen and the epithelial cell. And it does that by actively transporting sodium out of the epithelial cell and into the blood. Sodium is then able to diffuse down its concentration gradient through the co-transport protein, and as it does so, it brings glucose with it. Glucose here, we can see, is moving up the concentration gradient from a lower concentration here to a higher concentration here. That continues to happen as long as the sodium ions are moving down their concentration gradient. High concentration of glucose now in the epithelial cell, lower in the capillary, so the glucose moves out of the epithelial cell into the capillary by facilitated diffusion. As I said right at the start, the principle of co-transport is exactly the same for glucose, or it could be the same for an amino acid. The transport is determined by presence of these specific co-transport proteins which allow for some molecules to be co-transported, whereas others couldn't be. Now, okay, if you have any questions, if you've got any requests, can you leave them in the comments? I'm not going to put my email on here, just in case. Well, you can probably guess why. I think that's everything for co-transport. Thanks a lot.